Let's take a look at this specific example of a homogeneous first-order linear system. Now, this one is a 2x2 system. And just to see what that means, we're going to unpack the vector notation. So we're going to take it from this nice compact vector form and write out what all those vectors mean, and then perform the matrix vector product to get to something that looks like this. Now, this is what we will call a coupled linear system. It's coupled because the equation for x1 has both x1 and x2 in it. And the equation for x2 prime has both x1 and x2 in it. So this is a 2x2 linear system. And again, it's coupled, but we don't typically say that. We will always assume it's coupled. Now, our goal here is to say, what is the general solution for an n by n homogeneous linear system? I want to know every possible answer. Now, this is going to follow from ideas developed in linear algebra. If I take a homogeneous first order linear system, I can rewrite it in this way. And I'm going to introduce this notation, D, to stand for the differentiation operator. So an operator is something that takes a function as an input and spits out another function as an output. And in this case, it's going to take x, the vector, as an input and spit out x prime. The reason we like doing that is because it allows us to take this equation and write it in a very compact form. This is going to be written as Lx vector equals the 0 vector. L here is a linear operator. Now, because it's linear, it satisfies linearity, which means that if I were to put in two functions or two vectors, I could separate it out like this, which is really handy, as you're going to see in a moment. So to solve this system that we've been talking about is the same as saying find all solutions to this Lx equals 0. And effectively, what we're trying to do is find what's called a basis for the kernel of L, or you can think about it as some sort of null space. I want to find all the answers to this Lx equals 0. Okay, from linear algebra, we need to talk about a basis as a set of vectors that will, number one, create every answer in the solution set, and number two, be independent. So I have to have the right ones and just enough of them. Now, lots of things are going to get determined from this Lx equals 0. So if I have an n by n system, and let's say that x1, x2, all the way down to xn, these are solutions of Lx equals 0. What I'm going to do is consider this. Okay, well, let's take a linear combination of those solutions. C1, x1, C2, x2, all the way down to Cn, xn. That's a linear combination of solutions. Now, because L is linear, I'm now allowed to say, okay, this is going to be C1 times L1, or times L1 acting on X, C2, L acting on X2, all the way down to Cn acting, L acting on Xn. Well, each one of these things is a solution. That means each one of those terms is 0. And as you probably could have guessed from linear algebra, we get a 0. And what this is trying to tell me is a result. And we'll call this theorem 3.3-1, but it doesn't really matter. If these vectors, x1 through to xn, if this set, if these, it doesn't even have to be a set, I apologize, if these vectors solve our linear homogeneous first order system, then their linear combination also solves the system. It's also a solution. Now, that's not really a surprise. Now, there's a little note just for notation's sake from linear algebra. When we have this linear combination, remember that by definition of a matrix times a vector, I could think of this as a matrix whose columns are given by those vectors and multiplying by this. So we are going to call this thing capital X of t. That's going to stand for the matrix function whose columns are these solutions, and we'll call this vector x of c, or just call this vector of constants c. And that at least gives us a start. I know that this linear combination will appear somehow, and you're probably already able to guess how it's going to come about. So how do we find the general solution to this Lx equals 0? Well, we do it the same way that we did it earlier, and we are going to talk about the uniqueness theorem. The uniqueness theorem for initial value problems is going to save us here. So if I give you a first order system, we talked about the uniqueness theorem. There has to be a unique solution to this problem. Okay, so this implies the following, that x1 is the unique solution, so the only one, to this problem. So L of x equals 0, and we're going to take the initial condition to just be the vector whose entries are 1, 0, 0, 0 all the way down there. So you would know this as the fundamental or the basis vector E1. Let's say that E2 is the unique solution to the same initial value problem, except that the initial condition here is going to be E2, and then I can go all the way down to xn. This is going to be the unique solution to Lx equals 0, and the initial condition here will be En, so the last basis vector. So the uniqueness theorem tells me that I have to have unique answers to all of these problems. Okay, how does that help me? Well, this is going to get me that first step toward the general solution. So now let's consider this. So let's consider the general initial value problem. So Lx equals 0, and the initial condition here is just some vector of constants. And we'll call it x0, and whatever, it will be c1 all the way down to cn. How do we deal with this? Okay, there has to be a unique solution. The unique solution will be the following. The unique solution will be that linear combination we talked about before. And you say, well, why? How do you know that that's the unique solution? Okay, so by the theorem, by the uniqueness theorem, or actually not even by uniqueness, from above, from the linearity, we know that this c1 x1 all the way down to cn xn, this has to solve, this solves Lx equals 0. We already know that. That has to actually be a solution. Now, from the initial conditions, when I go ahead and I build this, each xi solves one component of the initial conditions. So for example, if I were to say c1 times the first solution, this is going to be C1 times E1. It has to satisfy that. C2 X2 T naught has to satisfy C2 E2 all the way down the list. Cn Xn T naught has to satisfy this. And that means that if I were to put them all together, this specific combination of functions will satisfy this. So let's recap. If I give you a general initial value problem, the uniqueness theorem tells me there has to be one and only one answer. I know that this combination will satisfy the differential equation, and by the argument above, this specific combination will also satisfy the initial conditions. And so that means that this C1 X1 of t all the way down to Cn Xn of t is the unique solution to that general IVP, and that means that this thing is what we are going to call the general solution to this L of x equals 0. I've shown you that there have to be n of these fundamental solutions, n of these solutions. They have to be formed this way. So that means this set spans the solutions, or the solution set of Lx equals 0. I will create every answer to this problem from these. Now, are they linearly independent? Okay. Linearly independent means that there's only the trivial solution to this combination equals 0. Now, when you're dealing with functions, you have to remember that this has to apply for any value of t. For all values of t. Okay. Well, it means if it has to apply for all values of t, that means in particular, it has to apply for some specific t naught. So that means C1 X1 of t naught all the way down to Cn X naught Xn of t naught has to be 0. Now, a subtle difference here is that these are vectors with functions in them. And when I put a specific value of t naught, these become vectors with numbers in them. Now, there isn't a huge distinction there, but what it's going to help you do is now come up with a tool to see whether or not these systems are linearly independent, because now you can use linear algebra. Or if I take this system and rewrite it in that form, capital X of t naught, the matrix, equals 0. And what I'm interested in is, does this have the trivial solution only? Now, from linear algebra, you will find that the trivial solution will only happen, it will be if and only if the determinant of this matrix is not 0. And that will mean this has to hold for any t naught. So this gives us a nice little test. And this is a test for linear independence. This set, x1 through to xn, this solution set is linearly independent if and only if the determinant of the matrix that holds all of those solutions as its columns isn't 0. And as before, we are going to call this thing the Wronskian. And if we put all of these things together, we have a way to check for a basis. If we find n solutions, x1 through to xn, these are going to be called a solution set. They will be linearly independent if the determinant of the matrix that holds these things as columns is non-zero. And then that means this set will be a basis. And we are going to call this, or a fundamental set. A fundamental set of solutions to our problem Lx equals 0. And in this case, the general solution to our differential system is C1 x1 all the way down to Cn xn. There have to be n of them for an n by n system, and we can test very easily. Now, as our specific example here that we talked about a little bit earlier, we have this matrix 3, 2, 4, 1 into the vector x. We found that one solution was e to the 5t 1, 1, and x2 was e to the minus t. Sorry, lost the value, e to the minus t negative 1, 2. Okay. Is this thing, x1, x2, a fundamental set? You're going to take a matrix, capital X of t. You're going to build it from x1 and x2. Those are going to be its columns. So capital X of t is going to be e to the 5t, e to the 5t, e to the minus e to the minus t, 2 e to the minus t. We are going to take the determinant of that matrix. It's going to be the determinant of the above. We'll get 2 e to the 4t, subtract negative e to the 4t, 3 e to the 4t. This will never be 0 for any t. And that means then this x1, x2 is a fundamental solution set. It's a fundamental set. And that means that the general solution to this system, 3, 2, 4, 1 with the x, is C1, so x of t will be C1 e to the 5t 1, 1 plus C2 e to the minus t negative 1 and 2. If we are given initial conditions, so let's say as an example, we were given these initial conditions, x of 0 is negative 1 and 8, we can find those constants, C1 and C2, by solving this. So x of t, remember, is going to be this capital X of t times our vector c there. And again, this is going to be C1 x1 plus C2 x2. And effectively, what we need to do is we need to solve x of 0 is this capital X of 0 times c equal to negative 1 and 8. So we need to solve this system. And if we were to put in those fundamental solutions, we'd have a 1, 1, negative 1 and 2, negative 1, 8. If we do the row reduction, we will find 1, 0, 0, 1, 2, and 3. So C1 would be 2, C2 would be 3, and the unique solution would be 2 e to the 5t 1, 1 plus 3 e to the negative t negative 1, 2. So it does work very similar to how other DEs worked. We just got through all the machinery to guarantee that it will work the same way.